Let's talk about reptile government. Let's talk about calculus. Calculus is all about rate of change of something. There are two types of calculus. There's differential calculus, which is what I'm mainly going to be talking about, which is all about cutting things into small pieces to see how it works. Let's imagine that you have a friend who is jumping off a diving board into a swimming pool and they're going to do a trick. You need to know exactly how fast they'll be moving at 5 seconds, say, 5 seconds after they jumped, so that you can ready your camera properly and take a photo of them that isn't all blurry and disgusting. So, how would we do that? Well, first of all, let's get a function, let's call it f of t, with t being the number of seconds he's been falling for, and let's say that is equal to the acceleration over 2 times t squared, and that will give us the amount of distance he's covered at t seconds. In this function, a is going to be roughly acceleration due to gravity, which is about 10, even though really we should make it 9.81 something something something. But for our purposes, let's just make it 10 over 2 times the number of seconds we've been falling for, squared, which of course is 5t squared. We want to work out the speed at 5 seconds. Now, speed is equal to distance over time. We know what time is. That's easy. That is 5 seconds. And we know how to work out distance now. That is going to be f of 5, which is going to be equal to 5 times 5 squared, which is 5 times 25, which is 125 over 5, which is equal to 25 meters per second at 5 seconds. But that isn't the exact speed he'll be moving at 5 seconds. That's going to be the average speed over the first 5 seconds. So let's work out the exact speed. So we've got distance over time again. What's the distance we've moved between 5 seconds and 5 seconds? Well, we can't really have any distance. It would be f of 5 subtract f of 5. And how much time has elapsed between 5 seconds and 5 seconds? Well, no time's elapsed. It's 5 minus 5, which gives us 0 divided by 0, which, oh, that's an issue. That's something we can't solve. So what do we do here if there's no distance moved and no time elapsed? Well, what we need to do is we need to create a unit of time so small that it doesn't matter. And we'll call that unit delta x. Let's rewrite our equation. We need to find the difference in distance between 5 seconds and 5 plus delta x seconds. Let's make that line longer. And the difference in time is delta x. So let's expand these. Now we've got, let's move it up here just because we've got a little bit more space. I don't like wasting paper. We've got 5.
Save the trees.
Save the trees. Save the trees indeed. I'm going to have like a little pop-up that says save the trees. So now we've got 5 times 5 plus delta x squared. Subtract 5 times 5 squared over delta x. And I'm just going to expand these quickly. If you want to know how I expand these, I'm going to put a little annotation on the screen right here to our video on binomial expansion. So now we've got 5 times 25 plus delta x squared plus 10 delta x subtract 125, oh, run out of space, over delta x, and finally that gives us 125 plus 5 delta x squared plus 50 delta x, and we take off this 125, that cancels that out here, over delta x gives us a grand total of 5 delta x plus 50. We want delta x to be so small that it doesn't matter, right? Ideally, we want no seconds to have elapsed, but we've got to settle for delta x seconds to have elapsed. Now, delta x can't be exactly 0 because we've divided by it here, and you can't divide by 0. But what's the limit as delta x approaches 0? The limit as delta x approaches 0 of 5 delta x plus 50 Well, it's equal to 50, isn't it? Because as delta x gets really close to 0, multiplying it by 5 will make no difference anymore, and this term will be cancelled out, leaving just 50. And this is double the speed that we had up here. So now, his exact speed after 5 seconds will be 50 meters per second, not 25 meters per second. So that was a problem where calculus is the only way to solve it. But let's talk about where it would be used in pure mathematics. And usually it's used to work out the slope at a specific point on the graph. For example, let's take our diver again. Here would be a graph of his distance over time. It would look something like this. Oh, that's supposed to be a straight curve. Not a straight curve. That's supposed to be a constant curve. Great. That's going to be his speed. And here is going to be 5 seconds. And this would be about 5 seconds. Mm-hmm. What we worked out the first time was the average slope between this point and this point, which looked something like this. What we wanted to work out was the exact slope at this point, which looked more like this. You can see the difference. Instead of working out the average slope between 2 points, differential calculus allows us to work out the exact slope at a specific point. As I said at the beginning of the video, calculus is all about rate of change. So let's say we have our function, let's call that f of t, and that is equal to the distance travelled at t seconds. And what we want to do, if we want to work out the rate of change of the distance, which is the speed at t seconds, we would have a little tick here, which means the derivative, which means after we pump the function through differential calculus. I'll explain how we do that in a second. So f tick of t, or derivative of f of t, that's going to be the speed. And then we add another tick to mean the second derivative, which means the rate of change of the speed, which is the acceleration. I probably spelt that wrong. Then we can have a third tick, the third derivative, which would be equal to the rate of change of acceleration, or the jerk. Then you can have a fourth derivative. You're probably getting the gist of it by here, and this is the jounce, the rate of change of the jerk. And you can have, if you have a changing jounce, you can have a fifth derivative, which will give you the rate of change to the jounce. I don't know what that's called, that probably has a name, but I don't know what it's called. If we work it out, we'll put an annotation on the screen, right about here somewhere. Yeah. So, that was weird. I am going to explain how we get each of these derivatives, how we get a derivative of a function. Let's say that our function, f of x, this now has nothing to do with distance and speed, we're just making any function. We'll make it 2x squared plus 5x plus 2. Let's make it a quadratic. And we want to get the derivative of it. We want to get the derivative of f of x. What we need to do is we need to find the difference between f of x and f of x plus delta x, which is the thing we're going to tend to 0. And we need to divide that by delta x, just like we did before. So that gives us, let's see, 2x plus delta x squared plus 5x plus delta x plus 2. Subtract 2x squared plus 5x plus 2. And we divide that all by delta x. Now that's a really ugly function. Of course we're going to expand that. I've shown you expanding this all before. I'm just going to cut here while I expand it. Okay, so I've expanded all of these now. This still looks really long and ugly, but don't worry, we're going to cancel out some of the expressions now. So this plus 2 here cancels out with this minus 2 here. This plus 5x cancels out with this minus 5x. This 2x squared cancels out with this minus 2x squared. And that's what we're left with. Now if we divide the remaining terms by delta x, we're left with 2 delta x plus 4x plus 5. And now what we do is we take the limit as delta x approaches 0 of 2 delta x plus 4x plus 5. And we know that that is equal to 4x plus 5. And so that is the derivative of 2x squared plus 5x plus 2. So the derivative of f of x is equal to 4x plus 5. So we can get a second derivative of this function. I'm not going to show you how to work that out, but that's equal to 4. So if we were to graph this function, the slope at x on the x-axis would be equal to 4x plus 5. And if we were to plot this function on a graph, the rate of change at x seconds would be 4. So no x involved. This graph would literally be a straight line. The slope would be equal at all points.